So we'll continue our discussion on fiber nonlinearities and specifically Kerr nonlinearity that we started last time. Okay, so basically we said that due to the Kerr nonlinearity, basically the refractive index becomes intensity dependent. Right. So this intensity is again we call power over the effective mode area. Right. So this is the nonlinear coefficient. So for silica glass, this was about 2.6 10 to the minus 20 meters square per watt. Right. And this, of course, is just the bare refractive index 1.45. Right. So basically this Kerr nonlinearity or intensity dependent refractive index gives rise to like three main nonlinear phenomena. So there is a question whether this quantity is always positive, such that basically the refractive index always increases. Right? So that's a good question. So for most materials, under most conditions, this is positive. Okay, but you can go into regimes in certain materials where you can actually get this to be negative. Okay. So that, without going into the details, which probably if you do a nonlinear optics course, we discuss in more detail, but basically this sort of the sign of this depends on the frequencies of the electromagnetic fields interacting, corresponding, and then versus the energy levels in the medium. Okay. So basically, if the frequencies interacting are sort of closer to being red detuned, like slightly lower than the energy level, or blue detuned slightly higher than the energy level, sort of depends on that. Okay. So here, of course, we are talking about, so the waves are propagating in the silica, and the wavelengths we're looking at are infrared, right? And the band gap of silica is very large, right? So the band gap corresponds to a wavelength in the UV. So the wavelengths are, or the photon energies are much smaller than the band gap. Okay, so we are talking about far red detuned waves, and for those waves, this is positive. Okay. And typically, that's the regime you work in most materials, because that's the transparency range of the material, right? Like if the optical waves have frequency lower than the band gap, then they're transparent, like the medium doesn't absorb, right? So typically we work in that regime, and in that case this is positive. So sort of this gives rise to three main effects, which we'll discuss sort of one by one. The first is called self-phase modulation. Okay, so of course you can see that if the refractive index is modified, then the phase that the wave acquires traveling through the medium depends on the refractive index, right? So of course this modifies the phase. So this term phase modulation, of course, makes sense. And this self here refers to that if you have a wave or a pulse propagating through the medium, then due to this nonlinear effect, it can modify its own phase. Okay, so that's why it's called self phase. So depending on its intensity, it modifies its own phase. So to see how that happens, so if you look at the propagation constant, right? So you know that we can write it like that, and basically, if we include this nonlinear term, then basically you have a correction to this, which depends on the nonlinear change in the refractive index. Okay. So if I write n here as sort of like the constant bare and not plus this intensity dependent term, then the second term will give me a correction to the propagation constant. right? So this is just the linear usual propagation constant, and this is the nonlinear part, okay? Which, so we write this as n2 times I, or n2 times P over A effective. Then I can write this factor as some gamma times the power, okay? And this gamma you can see from here is basically depends on the wavelength and this nonlinear coefficient and the effective mode area. Okay, so this is known as the effective nonlinearity of the medium. Or effective nonlinear coefficient. Right, so it has, of course, the material nonlinear index coefficient N2, plus also it has this mode area, right? So you can see that if you confine the mode to a smaller area, then this gamma is larger, right? Just because the intensity is larger. So, so this you can see has units of per length per power, right? So, so propagation constant is units of per length. On the right hand side, you have something, this gamma times power, which is watts. So this you can see has units of per length per watt. Right? So again, if we take like a typical single mode fiber used for telecommunications, then again, you know that this was about like let's say 70 microns squared at 1.55 micron. So then this gamma comes out to be about 1.3 per watt per kilometer. Okay. So, and typically for most fibers, for most silica-based optical fibers, this sort of lies between 1 and 5, like the conventional step index fibers. So there are some, depending on what your application is. For some cases, for example, for some particular nonlinear applications that not of course for telecommunications, but for like making some special light sources, etc., you want an enhanced nonlinearity. So that, for example, you can make this A effective much smaller. Okay, so you have these highly nonlinear fibers where gamma can be like an order of magnitude larger. Okay, and then you can go to some other materials, and like if you go to silicon waveguides, for example, you can make this A effective really small, like sub-micron square, and then this can go up by many orders of magnitude. Okay, but for our purposes, mostly for telecom applications, usually you want to suppress the nonlinear effects, right? Because they distort the signals that we are trying to communicate. So typically we want this number to be small. Right? Again, so if you use fibers with higher mode area, you can make this small. Okay, so now we know that the phase which is accumulated is just, so we know that the wave, so this mode acquires phase like this, right? So the phase is just beta z, right? So of course you have the usual phase, but then this additional phase due to the nonlinear effect. So if we look at the nonlinear phase, right? So that's basically if we integrate over the fiber length, this nonlinear propagation constant times z. Sorry, so right, and so if you put this, so gamma is a constant, so then here we have right, and if let's say we have linear loss, so an attenuation coefficient alpha, then the power will vary along the distance like this. Right? So then this is basically the same integral what we had for the computing the effective length, right? Effective nonlinear length. So you can see that basically this comes out to be this effective nonlinearity times the input power times the effective length. Okay? So you can now see how the effective length is useful here, right? So we just multiply the input power by the effective length. Okay, so you can see there is an additional phase here, right, which depends on this again effective nonlinearity, input power, and right. So you can immediately sort of see that, for example, if we do some modulation which is based on the phase, like phase shift key, right, or even maybe frequency shift key. So you have these schemes like BPSK, QPSK, right, where we encode information in the phase, like for example, 0 phase is bit 0, pi phase is bit 1, something like that. So you can see that because of this nonlinear, like there's an additional nonlinear phase, right, which will distort my encoded phase, right. So you can see it can directly, it will directly affect like phase encoding based schemes. But not only that, right, it also has an effect on even if we do encoding in intensity, right, just simple if you make pulses on off keying. To see that, so basically, so recall if you're sending pulses, right, so this power is also a function of time, right, so we are sending pulses, so this is some Gaussian kind of shape here. So this P is a function of time, right, which means the nonlinear phase is also a function of time. Right, so you can see basically as the power is varying through the pulse, the phase shift that is imparted at different points on the pulse will be different because. And you know that now if you have a time dependent phase, that means a frequency shift, right? Recall like when we were discussing dispersion, we had like a similar thing where we had eventually ended up with some time dependent phase, so which we could define as some change in frequency with time, which is a chirp, right? So similar case here. So if we define some instantaneous frequency shift, right, that's the derivative of this. So that you can see will go like the derivative of the pulse shape. Okay, so this is basically like a chirp, right? A time-dependent instantaneous frequency. So the value of that chirp depends on this derivative of the pulse, right? So you can see if I take the derivative, right? So here it's increasing. So it's positive here, then it's 0 at the peak, and then it becomes negative, right? So if I look at the instantaneous frequency, that looks like this. Sorry, there's a negative sign here, right? So basically I have to take the negative of this. So it looks like it. So derivative is positive here, so the instantaneous frequency is negative here. Right, so again, basically what we are saying is, so if you look at the electric field within the pulse, right, so there will be some change in the carrier frequency, right? With time, the carrier frequency won't be constant, but it will vary from the center frequency like that. So recall, like with dispersion, we had a linear frequency chirp. So if you assumed a Gaussian pulse, then we saw that because of dispersion, we ended up with a linear frequency chirp, right? So either positive or negative, depending on again the sign of the GVD of the fiber. So here we are seeing that because of nonlinearity, also there's a chirp, right? And you know that anytime you have a chirp, right, and now we are propagating through this fiber, then basically that can lead to pulse broadening, right? So basically, even if we have simple on-off keying like intensity modulation, even then the nonlinear this cell phase modulation can affect me by basically giving me sort of additional pulse broadening. Right? So you can see that so the nonlinear chirp is always of this sign. So right, this always, if you look at the middle of the pulse where most of the power is here near the peak, so it's linear with a positive slope. Okay, so this is like a positive chirp, right? So recall this happened. So if we had a dispersive fiber, right? If we had a fiber with beta 2 positive, right? So that resulted in the same kind of chirp. So if beta 2 was positive, then basically the chirp was also positive, right? So this corresponds to normal dispersion, whereas the opposite case for negative beta 2, the chirp was off, right? So if you can see that if we are propagating through a fiber which has normal dispersion, then the cell phase modulation will add the same chirp as the dispersion. So effectively, it will accelerate the dispersive broadening, right? So the pulse will broaden faster because of this nonlinearity than it would do just due to dispersion. Whereas if we had the opposite case, so if we had a fiber with anomalous dispersion, right, then this nonlinear chirp will actually compensate some of the dispersive chirp because it's of the opposite side. Okay, so in this case, nonlinearity can actually help. So for an anomalous dispersion fiber, right, beta 2 less than 0 or d greater than 0, you can see that effective chirp when we add these two will actually be smaller, right? And you can even imagine that if I set things up right, so of course this depends on the pulse, right? So it depends on the power, right? So this slope here for the nonlinear chirp depends on the power, right? You can see it's the derivative of the power. So if the power is just right, this slope can be exactly equal to this slope. Right, this slope is constant just given by the fiber GVT, and we can basically make them cancel each other exactly. Right. So when you do that, you can see that because of this interplay of dispersion and nonlinearity, effectively there is no chirp added, and the total chirp is 0, and the pulse propagates without any change. Right. So such pulses are known as solitons, where basically the dispersive chirp and the nonlinear chirp cancel each other out. Okay, so you can see that will happen only at a very particular power. And also not only that, actually, you can see that for the nonlinear chirp, it's only linear in this middle region, and then beyond that, it actually goes like nonlinear, whereas the dispersive chirp is always linear. Right? This is for the Gaussian pulse case, right? So you can imagine if you change the pulse shape here, then the dispersive pulse shape will also change because, right? So, for example, so we had, remember the propagation equation was, we had beta 2 times the second derivative of the pulse with respect to time. So it depends on the pulse shape also. So turns out that for Gaussian pulses, this exact cancellation cannot happen over the entire temporal range, but you can do this for what is known as a secant hyperbolic pulse. Okay. So basically, if your this pulse envelope was a secant hyperbolic, or something like this, instead of a Gaussian. right? Then basically it turns out that for some particular power here P naught, this cancellation can happen exactly, and this pulse will actually propagate without any change, even though the fiber has a non-zero dispersion and a non-zero nonlinearity. Okay, so you can immediately see that these pulses can be very useful for various things, right? Also for communications, right? So you basically cancelled out the effect of dispersion. But of course, it's a little bit more complicated than that, because you can see that the because of this linear loss, right? Even though I launch at the input with some particular power which satisfies the soliton criterion, then on propagation after some distance, you can see that the power will actually decay, right? And the soliton condition won't be met anymore. So this jerk will change because of the loss, right? So you can see that including loss, then the soliton condition is difficult to satisfy, but still there are some tricks we can do. Okay. Anyway, so even for intensity modulation, we can see that basically this nonlinear cell phase modulation gives rise to a frequency curve, which can give me either additional broadening or mitigate the dispersive broadening. Okay, so typically, I mean, you design your communication system such that this nonlinear phase shift is small, so that you can neglect any effect due to this, like either on the absolute phase if you're encoding information in phase, or in the pulse broadening due to the chip. So again, if you imagine a long link with many amplifiers in between, right? So then this L effective, recall, is basically the number of amplifiers here divided by alpha, where 1 over alpha is the effective length of each section here, right? So this also I can write as L over LA. That's the number of sections here. So typically we want the total nonlinear phase shift to be less than 0.1 radian, okay, over the link from the transmitter to the receiver. Right. So for example, if you look at, I mean, if you know, like if you have a BPSK constellation diagram, right? So this is bit 0, so there's 0 phase and pi phase, right? And then due to the distortion in the fiber, basically you don't get a spot, but you get a spread due to the distortions, right? So here basically this cell phase modulation is acting like a distortion on your phase, right? So basically if you say that, okay, if this is less than 0.1, right, I can still make a good decision between whether it's bit 0 or bit 1. Okay, so if we put this expression here, L effective, and then L effective, we put this value, then this condition just means that your input power is now, so all these other values are constant for the link, right? So your input power is now restricted to less than a particular value. Or I can also write this as in terms of the link length. Right, so you can see that if I want to have a longer link, then I have to reduce my power. Like similar to, for example, what we had for the Raman scattering, right? There, of course, the effect was different, but again, due to this, there we had this crosstalk that put a limitation on the power we can send in the bit, right, or in the optical pulse. Similarly here, this phase condition gives me a limit on the power I can set. Right? So to maintain the same SNR and a low bit error rates, I want to typically, if I increase L, I want to increase P. Right? But due to this nonlinear distortion, we can see that I'm actually not allowed to do that. So if you again put some typical numbers here, so for example, gamma 2 per watt per kilometer, let's say you have 10 amplifiers in the link, and alpha 0.2 dB per kilometer. Right, so typically like there's amplifier spacing is again like 50 to 100 kilometers. So let's say if it's 100 kilometers, this would mean like a 1000 kilometer link. Then you can see that the input power has to be less than about 2 milliwatts. Okay, so you can see that's a very strong condition here now, because again, typically the powers that we want to use in the optical communication system typically is, as we saw, was like maybe tens of milliwatts. Right? So you can see that yeah, at those power levels already there is some non-negligible effect of this self-phase modulation. Okay, and then basically a related effect for the self-phase modulation. So the self-phase modulation again will be important sort of for each wavelength channel, right? So this is the phase induced by the pulse on itself, right? So it's basically each channel distorting itself, right? But there's a related effect if you have again multiple channels traveling through the same fiber, then they can also like one wavelength can also impose a phase shift on the on a different wavelength, okay, due to the same mechanism, right? So we saw the refractive index was dependent on intensity. So what can happen is that the intensity is now modified by the pulse at a particular wavelength lambda 1, right? So it modifies the refractive index, but this modified refractive index is seen by the other pulse also at a different wavelength, right? So you can see that now basically the intensity of pulse at lambda 1 will cause a phase shift for the pulse at lambda 2, right, due to the same kind of effect. So that's known as cross phase modulation, right, because now it's sort of one wave causing a phase shift on another wave. But yeah, fundamentally the origin of the effect is the same. Right, so now let's say I have some n channels all propagating through the fiber, right? Then if I look at the nonlinear phase shift for the jth channel, so if we have to take some jth channel here and look at the nonlinear phase shift that it experiences, then of course it will see self-phase modulation, right, due to its own intensity. Plus, now it also experiences cross-phase modulation from the other channels. Okay, and there's a technicality here that the cross-phase modulation is actually a factor of 2 larger than the self-phase modulation. Okay, and this is basically coming from sort of like the symmetries involved in the nonlinear interaction. And basically there are twice as many ways or permutations of the waves interacting in the cross-phase modulation case versus just a single wave interacting with itself in the self-phase modulation case. Okay, so that's a factor of 2. Yeah, so we are not discussing this in detail, but again, for that, if you do a nonlinear optics course, then the origin of this 2 will be discussed in more detail. But for now, yeah, you can just think of it as there are twice as many ways of this nonlinear interaction happening between 2 different wavelengths as opposed to the self interaction happening. So that's a factor of 2. But otherwise, the form is the same: gamma times the power times the effective. But except now the power is now of the other channel, because it's the other channel which is modifying the refractive index, and this jth channel is now seeing the change in the refractive index, which modifies its own phase. Okay, so of course now you can see with cross-phase modulation this effect is much worse, right? All the other channels are affecting me now more. So again, you can see that there will be a corresponding chirp or frequency shift. Right, so which will again depend on sort of the derivative of these pulse shapes here. Okay, so I mean, if you take the typical case where all channels have sort of like the equal powers at the input, and then this nonlinear phase shift here, you can see. So if I just talk about a single link without any amplifiers in between, so basically all these powers are equal. So if it does do this summation, we'll get this. So right, M is the total number of wavelength channels. So P is the input power per channel. Okay, so this is again for no amplifiers. If you have amplifiers in the link, then you'll get a factor of n here. Right? So if you have amplifiers, then you multiply this by n number of amplifiers because their effective length is multiplied by the number of amplifiers. Okay, so this is sort of the worst case scenario, right? So you can see that it's sort of like it's worse by a factor of 2m minus 1, where m is the total number of channels compared to just self-phase modulation. Because yeah, you have m minus 1 other channels also influencing you. So, so this is the worst case. This is for all the different channels are overlapped, right? So you have these pulses. So this is at lambda 1, lambda 2, lambda 3, lambda 4, right? So let's say even if at the input they are sort of launched together, we are assuming that they stay overlapped all through the fiber. Right? But of course, you know that if because of dispersion, right? So these different wavelengths will travel at different velocities because of dispersion, right? So after some point, basically they'll start right moving away from each other, and they won't be overlapped anymore. And once they're not overlapped anymore, you can see that. So if this pulse causes a change in the refractive index, this pulse is not here yet to experience this change in refractive index, right? So now this can't influence this pulse. So only when they are overlapping will we see this phase modulation effect, right? So, but actually due to dispersion, what happens is that these pulses don't perfectly overlap as they propagate along the path. Okay. So then the phase shift will actually be smaller than this. Okay, so if you want to fully model like what's going on because of this surface cross phase modulation and dispersion together in the fiber channel, right? So what briefly we sort of discussed that okay, there is a chirp from the dispersion, there is a chirp from the nonlinearity, and they can either add up if they are of the same sign or subtract. But for a general case, if you want to calculate what really happens to the pulse that is propagating, like we did for the dispersion case, then basically we have to go back to like the pulse propagation equation, right, and include a nonlinear term. Okay, so basically the pulse propagation equation we had just due to dispersion was so right. If we had GVD, then it was like this. Right. So if beta 2 was the dominant term, then basically this was the pulse propagation equation. If you are working near the zero dispersion point, then we can add like the next higher order term here. For example, right? So this was just due to dispersion. So now we can add more terms to this propagation equation if you want to include more effects, right? So for example, if you just want to include linear loss, you can add like a linear loss term, just a simple propagation loss. So alpha by 2 because this is the amplitude, right, which is the square root of the intensity of power. And then if you want to include this Kerr nonlinear term also, we can do that, right? So that recall that's like a phase shift here, right? So we get a phase shift e to the I nonlinear, right? So we get a phase shift on the pulse, right? So this basically we can write as, so if we take dA by dz, then basically we get a I nonlinear phase times A, right? So for dA by dz, basically if we add this nonlinear I times nonlinear phase, right? And nonlinear phase was again this was gamma times P, right? So and P is basically just mod A square, right? So if we normalize the amplitude units such that mod A square gives me power, right? Then I can just write this as mod A square times A. So this was basically beta nonlinear times Z. So this will be beta nonlinear, which is gamma 3. Right. So by adding this term here, right. So now you can see this is a nonlinear term in A. Right. All the other terms are sort of linear in A. But here you have a mod A square times A. So it's cubic in A. Okay. So that's fundamentally again because this Kerr nonlinearity is what is known as a third order nonlinearity. Okay. So you can see that the power of A is 3 here, cubed. So that's the third order nonlinearity. So You can imagine that there could be, for example, a second order nonlinearity where like you have some term which is proportional to a square, but turns out that due to some fundamental, again, symmetry arguments, if you have an isotropic medium like glass, it's an amorphous medium and it looks the same in every direction, then turns out for such a medium, specifically which satisfies the so-called invergent symmetry. Okay, so if I invert the medium about some particular point, then the medium looks the same. Okay, for such a medium, basically the second order nonlinearity vanishes. So basically for glass, we don't have any second order nonlinearity, and the first nonlinearity which shows up is third order. Okay, but anyway, so you can modify the pulse propagation equation like that. Now, of course, it becomes much more complicated to solve, and typically you use numerical techniques to sort of solve this. Okay, so basically you have dispersion here. This is linear loss, right? This is Kerr. Right, so if you really want to see exactly what is happening to the pulse, both in time and frequency domain, and then basically you have to solve this propagation. So yeah, so this phase modulation or Kerr effect can also be used to build certain like all optical devices, right? So for example, like in the communication case, of course, we are treating this as a problem which is distorting our signal, but it can actually be used to build some useful devices. So for example, so in the beginning of the course, we discussed that typically how signals are encoded into this optical domain is like through time division multiplexing, right? So typically, like if you have some video signal or something, the effective bit rate, data rate required for that video signal is much smaller than the bandwidth per channel that we are using in the optical case, right? So for example, for the video channel, you only need, let's say, 100 megabit per second for each video channel, for each video signal. But here we have 40 gigabit per second on each wavelength channel, right? So basically what we do is we can send multiple video channels together on the same channel, right? On the same wavelength channel. And how we do that is just time division multiplexing. So basically if you're, so this is 1 over your video bit period, right? So let's say for argument's sake, it's 1 nanosecond. It's one gigabit per second, let's say, which is on the higher end for video, but let's just assume that for now. So this is 1 nanosecond here, right? And then my optical pulse period is, so for 40 gigabit per second, it's 1 over 40 nanoseconds, right? Or 25 picoseconds. So I can basically fit in 40 pulses here in one. So basically what I can do is I can simultaneously send 40 different video channels, right? And then in the next, after a bit period for 1 nanosecond, basically now I have the second bit of the first channel, right? And then so on. So this is called time division multiplexing, right? So different time slots. So the first slot is for the first video channel, second slot is the second video channel, right? And so on. So now the question is, like, for example, how do you demultiplex this, right? So of course you can have some electronic algorithm at the receiver end. You sort of detect the pulses, all the pulses, and then have some decoding set. The first channel is for the first, like the first pulse is for the first channel, and then after 40 pulses you sort of go back to the first channel. But you can also sort of pick out different channels here optically. Okay, so and this you want to do so. For example, as the speeds go up, right, it becomes more and more difficult for the electronics to sort of follow these very short pulses, right, and then do this electronic processing in real time at high speed. So if you can do everything almost optically, then that's always better. Okay, so people are always looking to do more and more things optically and less things electronically. So to pick out these different channels, you can so you can make a Mach-Zehnder interferometer. Okay, so here you have your bit stream coming in, and let's say you set up this interferometer such that basically the path lengths are set up such that you have destructive interference to come out of this path, but constructive interference to come out of this path. So basically your data is coming out of this arm. Okay, but now let's say I want to pick out some particular channel, like channel 1 or channel 4. I only want to pick out that particular channel to send it to somewhere else. Okay, so then basically what you can do is use this cell phase modulation. So what you can do is, so you have a section of fiber where, okay, so I send another pulse train here, which has basically, right, whose repetition rate is basically the bit rate of the video stream, right? And I have the delay such that this lines up with whatever particular channel I want. Okay, so by having some delay on here, I can change which pulse the overlap happens with which channel. Okay, and basically the power you set is such that the cross phase modulation that this pulse imposes on the data pulse is pi. Okay, so with this formula, of course, there's only one. So I'm just looking at cross phase modulation. So just one particular power here. Okay, so basically you neglect this, and you don't have a sum here. You just have p. So if you make that number equal to pi, right, by controlling this power and the length over which this interaction happens here, then basically you can see that whenever the pulse is present here, the data pulse will acquire an extra pi phase shift. Okay, so instead of being constructively interfered on this path, it will become destructive, and then it will come out of the other path. So whenever the pulse, this extra external pulse train you're sending overlaps with your data, that particular data pulse comes out of the other port, right? Because for that particular pulse, there is an extra pi phase. For the other pulses which happen here, it doesn't see any pump pulse, right? So that is, so you can see how you can pick out different channels like this. Right, so basically you can make all optical switches like this using this Kerr nonlinearity or cross phase modulation. Okay, and now basically there is no limit on like the speeds at which you can operate. For example, this Kerr nonlinearity, as we discussed, was almost instantaneous, right? So in principle, if you can make shorter and shorter pulses here, you can do this for faster and faster bit streams. Whereas for electronics, you are limited by the detector bandwidths, the electronic whatever components you use, their bandwidth. Okay, so then one another effect that this Kerr nonlinearity gives, in addition to this phase modulation, is known as four-way mixing. So as the name suggests, that it's a mixing between different waves at different wavelengths or different frequencies. So for example, it will be important for FWM systems where and introduce crosstalk in FWM systems due to mixing between different wavelength channels. Okay, so hopefully, yeah, this cell phase and cross phase modulation is clear. Any questions on that? Yeah. So then the next effect that this Kerr nonlinearity gives is called four-way mixing, right? So basically, as the name suggests, what's happening here is that four different waves, for example, at four different frequencies or wavelengths, are sort of mixing with each other. Okay, so typically that's denoted by some diagram like this. Okay, so let's say you have frequencies nu1, nu2, nu3, and nu4. Okay, so you can sort of think of the process something like the material. So this is some electronic energy level here, right? So the material absorbs one photon from of frequency nu1, another photon of frequency nu2, and then emits a photon of frequency nu3 and another photon of frequency nu4 and comes back to its initial state. Okay. So of course this happens very fast, almost instantaneously. Okay. So it's not that it's going to another energy level here. So there is no energy level here. So this is sometimes called a virtual level. Okay. So there is no energy level here, but basically instantaneously almost like it absorbs. I mean, the word absorbs is not accurate, but you can almost think of it like as if it absorbs these two and immediately emits these two. Okay, and then the frequencies, if they add up like this, right? So the photon energy we know is h nu. So the energy of these two, if they add up to the energy of these two, then basically it will come back to its initial form, right? And then energy is conserved, right? So in effect, what has happened is that we've transferred some energy from these channels 1 and 2 to channels 3 and 4, right? So we've taken out some energy from 1 and 2 because those photons are annihilated, and photons at 3 and 4 are emitted. So 3 and 4 channels now experience some increase in power. Okay, so in general, this is the process, right? So if you have 4 different frequencies or wavelengths like this, right? So in terms of wavelength, the condition is this. Right, then you can have this kind of process happen, which can transfer energy between different frequencies. And again, why 4 here is because again this Kerr nonlinearity is a third order nonlinearity. Okay, and again, if you go back to the basics of nonlinear optics, an nth order nonlinearity gives rise to n plus 1 wave mixing. Okay, so third order nonlinearity gives rise to 4 wave mixing. So that's why 4 wave mixing. Anyway, yeah. You can also see that, like for example, you can create new frequencies. So let's say I had only channel 1, 2, 3 present in my fiber. Then due to this interaction, basically a new frequency, nu4 is generated, which is not present in my input signal. Okay, so So if all these 4 different frequencies are different, it's called non-degenerate. So four-way mixing is shortened to FWM. Okay, so it's known as non-degenerate four-way mixing if basically all these frequencies are different. So specifically, if these two input frequencies are not equal, are different, then it's called non-degenerate. And if they are equal, then it's called degenerate. Okay, so I mean, from this four-way mixing process, you could effectively have a three-way mixing if these two frequencies are the same, right? So these two photons could come from the same wave, right? So you could have nu1, nu1, and then you could have nu2, nu3, right? So effectively, there are only 3 frequencies involved, but fundamentally, it's a four-way mixing. Okay, so this is a degenerate four-way mixing. This is a non-degenerate. So you can see basically the frequencies have to be symmetrically placed, right? So here basically, so the average of nu1 and nu2 is the same as average of nu3 and nu4. So nu1 and nu2, they're like this. Then nu3 and nu4 are symmetrically placed about some center, right? In the degenerate case, basically the center is just this frequency because the average of nu1 and nu1 is nu1, and then nu2 and nu3 are symmetrically placed. So these detunings are, so this is some delta and this is some capital delta. So here there's only one delta. Okay, for this energy conservation condition to be satisfied. And of course, this is the case when, for example, if you have a WDM grid, we are sending a grid of wavelengths, and typically they are all equally spaced, right, in frequency. So again, for the DWDM grid, we have delta is equal to 100 gigahertz, right? So typically we have this case when we are sending multiple channels. So you can see basically, so in this case, energy can be transferred from nu1 to nu2 and nu3 due to this process. Right? So something similar like what we had in the Raman scattering case, energy being exchanged between wavelengths, just how it's happening is slightly different, right? The process is fundamentally different. So in the Raman case, higher frequencies always scattered to lower frequencies. In this case, you can see one frequency scatters to both higher and lower frequencies. Okay, so in addition, so for any physical process to happen, from your fundamental physics, you know that in addition to energy conservation, you also need momentum conservation. Right? And momentum for photons is basically just wave vector. Right? So you know momentum of a photon is h bar times k, where k is the wave vector. So in the fiber case, basically we have this propagation constant beta. Right? So for this process to happen, you also need what is known as momentum conservation or phase matching. Right, basically because momentum is basically wave vector for optical waves, and wave vector basically is phase, right? Phase shift gives a phase shift. So just like this energy conservation condition here, the input momentum and the output momentum has to be equal, right? So that's the total momentum for the output waves, right? Beta at omega 4 and beta at omega 3. And if you subtract the input momentum, basically we want this to be 0, right? For momentum to be conserved. So just like nu1 plus nu2 has to be equal to nu3 plus nu4, beta 1 plus beta 2 has, or beta at omega 1 plus beta at omega 2 has to be equal to beta at omega 3 plus beta 2. Okay. So I put, instead of an equal to, I put like a tilde here, saying that actually what happens is that like if you have like classical mechanics, for example, balls colliding, you might have done this in your bachelor's mechanics courses, right? You have these masses coming, colliding and going away, and then you can compute things by using energy and momentum conservation. And there you use exact conservation, right? So you use exact momentum conservation. But here for these optical waves, because they're waves, also coming fundamentally from quantum mechanics, due to this uncertainty between momentum and position, right? So you can't define the position. So for balls or some masses coming, the position is well defined. They are like rigid masses. But for these waves, the position is not well defined. So it turns out from the uncertainty relation, the momentum is also not well defined, which means that you can actually have some slight mismatch in the momentum and the process will still happen. Of course, the efficiency will go down, but it's not like classical mechanics where you need exact conservation. Some slight deviation due to the uncertainty principle is allowed. So we'll see what that depends on. So let's take a degenerate case, because typically this is more efficient than this non-degenerate process. Okay, so for the degenerate process, so right, so I can write omega 1 and then say omega 3 and omega 4, like that. Okay, so typically this input waves are again called pump from conventional nonlinear optics terminology. And then these output waves are called signal and idler. Okay, so you can see that, so basically since they are symmetrically placed here, right, from energy conservation. So if the frequency separation here is some capital omega, so omega 3 is basically omega 1 plus capital omega and omega 4 is omega 1 minus capital, so that the sum is 2. Okay, and so we can compute what this delta beta momentum mismatch between the output and the input waves is depending on the frequency spacing or the channel spacing here, right? So again, this beta is a function of frequency, right? Dispersion. So you can imagine that again we can use this Taylor expansion, right, and try to compute this delta beta, the phase mismatch, as a function of this frequency spacing, right? So for example, basically if you take, so since omega 1 is the center frequency, so basically, and I'm looking at plus minus from that center frequency, I use Taylor expansion. So typically, of course, again, this is valid because now the channel spacing is much smaller than the frequency, right? So again, channel frequency, we're talking about 100 gigahertz, hundreds of gigahertz in that range, whereas this absolute frequency here, you know, is in hundreds of terahertz, right? So this is much smaller than this, so we can use a Taylor expansion about omega 1. So the first term will be beta 1, right, which is the first derivative of beta, or inverse of the group velocity, times frequency separation. So now for plus minus, this will be plus minus here. And then the second term will be again the GVD term, the second derivative of beta, times omega square. right? And now for plus minus, since we take a square, for both we get plus, right? So basically for beta at omega 4, I can substitute this expression, right? Omega 4 is just omega 1 plus capital omega. So I can substitute this expression. Similarly for omega 3, just plus minus here sign change will happen. So when you do this now and calculate delta beta, first of all you can see that the beta at omega 1 terms will cancel out, right? So we're again looking at this degenerate case. So omega 1 is equal to omega 2. So this is 2 beta at omega 1. And from here also we'll get 2 times beta at omega 1. So that will cancel. Then the first order term, for omega 4 it will be minus, for omega 3 it will be plus. So that first order term will also cancel out. Right? The only term which will survive is the second order term. For both these it will be plus, so that will have, right? So basically this delta beta just comes out to be, if we include terms up to GVD second order, will just be beta 2 times omega square. Right, so you can see that as I increase the frequency spacing here, this momentum mismatch increases for a particular GVD of the fiber. Okay, so you can see if the GVD of the fiber, let's say if you're operating near zero dispersion, where beta 2 is very small, then I can go to very large frequency spacings without making this too big. Okay, so again, sort of like a rule of thumb you can imagine is that if the cumulative phase difference, so delta beta times L effective, right? So this difference in the wave vectors multiplied by the effective nonlinear length, if that's less than pi, then basically the process still sort of constructively interferes over the fiber length, and this process is efficient. Okay. So you can see that basically I want my delta beta smaller than a particular number, right? If it's smaller than that number, which gives me a frequency range given my beta 2 value, then for that frequency range, this four-way mixing can happen. And you can see that if the dispersion is smaller, then this can happen for a wider frequency range. Okay. So let's say if you have additional channels here, it could also happen for that. These could also mix. So basically the point is that if you want to suppress four-way mixing, if you want to suppress the crosstalk between different channels due to four-way mixing, then you'd actually need a large value of beta 2 or large dispersion, right? Basically you want, ideally what you want is that if you go even to the first channel, this delta beta should become such that this delta beta times L becomes larger than pi, right? So even for the first channel, this process is not phase matched. So this transfer of power does not happen. Okay, so you can see that you need some large beta 2 here. Okay, so this is basically contrary to what you want just from linear dispersive effects, right? For that you want a small beta 2 to avoid intersignal interference due to just linear dispersive effect. But if you have a small dispersion, you can see here that the four-way mixing effect will be large. Or over wider channel. Okay, so like so if you have many channels, then you could have like the degenerate process. You could also have the non-degenerate process where these two sort of act as pumps, and then these two act as signal and idler, right? So for these equally spaced channels, you can have both the degenerate and the non-degenerate happening together between various channels. Anyway, so if, in general, if you look at, so like these, if you have these 4 channels mixing with each other, okay. So let's call this 4, 1, 2, 3. Then the, so if you look at this process, right? So if I have some powers in the channel 1, 2, and 3, and I want to see, because of this process, how much power gets transferred to 4. Okay, I can write that as some 4-way mixing efficiency times this gamma times length of fiber square times the powers in the 3 channels. So P in 1, P in 2, P in 3. Okay, so this is again coming like because of this third order effect, right? So the power transferred to channel 4 is a product of, so we have 3 factors of power here. Okay, and then an attenuation coefficient if you have some linear loss in the fiber. Okay, so this 4-way mixing efficiency here depends on this dispersion coefficient, so this phase mismatch, and the linear loss alpha. Right, so you can imagine if the fiber has either large loss, right? Loss means the powers due to just linear loss decay very fast, so this nonlinear interaction is weak, right? So either large loss or large delta beta here or large dispersion. In both cases, this efficiency will be small, right? So for large efficiency, you want low loss and low dispersion. So loss in any case is, I mean, for optical fibers, it's very small, right? This gamma is the same gamma we had for the cell phase modulation case. So this is the effective nonlinearity, which is 2 pi over lambda, the nonlinear index divided by A. Okay. So you can see it's fundamentally coming from the same effect. This N2 is coming here. This is the same gamma. Okay, so specifically this four-way mixing efficiency eta can be written as okay. So you can see that, right? We have exponents here for alpha and delta beta. So if alpha or delta beta or both are large, then this value is small. So you can check. So for example, if delta beta is 0, right? So in the case where somehow you have perfect phase matching, then this basically is e to the, so this is 1 minus e to the minus alpha L by alpha L, right? So this reminds you of something, right? So what is 1 minus e to the minus alpha L by alpha? That is L effective. Okay, so that's just L effective by L. So it's mod square, so we get square. right? So for perfect phase matching, this efficiency factor is just the effective nonlinear length divided by the total fiber length. So if you put this eta here, you can see the L squares will cancel, and I'll just get L effective square. Right, so again I'll get something gamma times power times L effective raised to some power. Okay, but if you have delta beta also non-zero in the general case, then this factor is more complicated like that. Right, so again delta beta basically we can estimate as the GVD coefficient times the channel spacing square. Right, so this omega here is basically 2 pi delta F channel. So we can plot this four-way mixing efficiency, right? This is basically how much power, fraction of power we are transferring to this 4 channel from 1 to 3. As a function of this channel separation. Okay, so here you have channel separation in gigahertz. Right, so the modern DWDM grid is 100 gigahertz spacing. Okay, so how the efficiency falls with, so as you increase channel spacing, you can see that for a particular GVD coefficient, this delta beta will increase, which will decrease this eta, right? So this eta falls with increasing channel coefficient. So, for example, if you work at low dispersion, okay, so this is, for example, with dispersion coefficient of 1 picosecond per nanometer kilometer. Okay, so you can see that this bandwidth is, let's say, up to 100 gigahertz, right? So if your channel spacing is less than 100 gigahertz, then four-way mixing is quite efficient, and there'll be quite a large amount of crosstalk. Right, so if you want to operate at this low value of dispersion, then your channel spacing has to be large, beyond, let's say, 200 gigahertz. Right? If you increase the dispersion, then you can shift this curve to smaller values like that. So this is, for example, at the usual value of 16 picosecond per nanometer kilometer. Right? So this is the value for standard SMF at 1.55 micron. Right, so you can see that for that case, so in the C-band wavelengths, if you use a conventional SMF, the dispersion is large enough that if you lose, for example, 100 gigahertz channel spacing, then you don't have any crosstalk due to four-way mixing. But then you have to compensate for the dispersive effect, the linear dispersion. Somehow, like at the receiver or something, right? So you can see this trade-off between sort of this linear dispersion and this four-way mixing crosstalk. Right. Another solution that you can do is like have locally large values of dispersion, but averaged over the link have a very small dispersion, such that the overall linear dispersion broadening is small. Right. So, for example, you can alternate between large and small, or positive and negative values of dispersion. Right. So, if you have a long link, you just alternate between. So here you have plus d, then you have minus d, plus d, right? So this D value is large, let's say 16 or 20 or something. So locally, right, the dispersion value is large, so there is no four-way mixing. Right, so this does not depend on the sign. It could be positive or negative. Right? You can see it's like magnitude here, so it doesn't depend on the sign of beta 2. It could be positive or negative. The efficiency is the same. Yeah, so in each of these sections, basically, if the D is large, you've sort of eliminated four-way mixing, but because of this inversion, overall average, because so the broadening which has happened here will be compensated by the negative dispersion here, right? So overall, you also compensate for the linear dispersive broadening along with four-way mixing if you have these locally high value of dispersion, large value of dispersion, but average over the link near zero value of dispersion. Okay, so yeah, so that's in terms of communication, like basically you want to avoid this crosstalk due to four-way mixing, but again, four-way mixing can also be useful for certain particular devices or elements that you want to make, right? So so one thing is, for example, if I want to sort of put the data or I want to take the data from one particular wavelength channel and put it onto another different wavelength channel. Let's say I have some large optical network in a particular section of the network. You want to use one particular wavelength because of the fibers and the components that are used in that particular part of the network. Once you go to some other part of the network, then basically maybe you're using some other components which are more efficient at another wavelength or something, right? So then basically you want to transfer your data to this different wavelength. Right? So of course you can do it by first detecting the data, converting to electronic form, then again remodulating the data with a new laser at the new wavelength, right? But again, you do this optical to electrical and electrical to optical conversion. It's limited in speed. Let's add noise, etc. So if you can do this all optically, then again, it's much better, right? So you can see here in four-way mixing, you can do that straightforward, right? So I have some data, let's say in this channel 1 here. So I just use like continuous wave laser. So I can even do degenerate, for example. So I just need one continuous wave laser and then one another wavelength which has my data on it, right? And then from this four-way mixing, basically it will get this data will get transferred to this other wavelength, right? So this new wavelength will now have the data. So you can easily sort of transfer data from one wavelength to another using four-way mixing. That's one application there straight away. And again, this you can also do this demultiplexing of TDM signals that we talked about with cross-phase modulation. You can do the same thing with a four-way mixing, right? So again, let's say you have now a pump pulse frame which has a repetition rate at the signal you want to demultiplex, right? And if this is the pump or omega-1 here, right? And you line up with your signal or omega-2 here. So depending on, again, the delay, you can line your pump pulse up with whatever time division channel you want. And then if you look at the idler which is generated, right, that will only happen when the pump pulse is present, right? So you can demultiplex. So if you delay this now, you can hook up the second channel. You can pick up individual TDM channels from a TDM signal. Just like so, that's another application. Another interesting application is actually also for dispersion compensation. So actually, what happens is that So we talked about the powers here, but if you look at the amplitudes for this kind of process, right? So if you look at the amplitude at this fourth frequency, which is generated, that's proportional to sort of A1 square times the conjugate of A3. Okay, so there is a phase conjugation happening here. Okay, so you can sort of think of upward arrows as being the signals, and then the downward arrows being the conjugates. Again, we won't go into details of where this is coming from, but basically you can write the amplitude of this idler wave like this. So square of the amplitude of the pump wave times the conjugate of the signal amplitude. So you can see if I take mod square, then I get the power, and then I get something like this, right? So P1 and P2 will be the same, so I'll get P1 square and then P3. So if I take mod square on both sides, but the amplitude is like this, okay? And this conjugate is very useful, right? So for example, let's say you have a link, right? So and you get some dispersive broadening, right? And typically we saw that basically that broadening depended on this GVD value times the length, right? So basically we acquired some phase like this, right? So the spectrum was multiplied by some phase like this, which was basically giving me the broadening. So one dispersion compensation technique is actually known as optical phase conjugation. Okay, so there what you do is in the middle of the link here, right, like L by 2, you do four-way mixing with like, so in this locally you have a strong pump wave here, and you do four-way mixing, and you basically send forward the idler from here on. So you have the signal frequency coming from here, right? So again, so your input had some spectrum, right? And then at the halfway stage, basically we get this, right? So due to the dispersion, you multiply by a phase like that at the halfway stage, right? And now due to this four-way mixing, basically the idler that you generate is the conjugate of this. Okay, so you take conjugate, right? So you get a minus sign, right? Because so the idler generated is the conjugate of the signal. So the idler spectrum looks like this. So it has a minus. The idler generated has a minus, so its phase is opposite with frequency, like the phase sign is opposite, right? So so now if you send the idler forward, you can immediately see now in the next half here, you'll add the dispersive phase shift, which will be the positive sign because of beta 2, right? And these two will cancel out, so you'll get back your initial spectrum, right? Or when you convert back to time, you get the initial pulse again. Right, so basically you eliminated, so here you get some broadening, but then it comes back to the original pulse because of this phase conjugation due to four-way mixing. Okay. Because of this conjugate, basically reverse the phase shift, which then cancels the phase shift in the next half. Okay, so this optical phase conjugation is basically a technique that you can use, employing four-way mixing to compensate for dispersion. Okay, went a few minutes over time, so we'll stop here. Yeah, I think with that, basically, our discussion on nonlinear effects in the optical fiber channel come to an end. And with that, basically, in general, the characteristics of the optical fiber channel, we've discussed everything there is. So we'll move on to the next section next important building block of the optical communication system, which is the optical transmitter. Okay. So this basically finishes our discussion on the channel. Now from the next class, we'll move on to the transmitter. Any questions? So we skipped over some of the basic fundamentals or details of these nonlinear interactions and just sort of used the important results to apply in a communication system. But yeah, if you are more interested in like the fundamentals and origins of these nonlinearities and how to model them, then a course on nonlinear optics would be useful for that.